you can follow along. I don't know how fast Matthew is at typing. So a little bit of introduction about me. I'm a software engineer over at Microsoft now, graduated from UCF last semester, was really big fan of Night Hacks throughout there. Night Hacks was a great club, and I've done plenty of workshops in the past, so you might recognize me. I'll pass it over to Matt so he can introduce himself.
Hi, everyone. I'm Matthew Villegas. I'm also a software engineer at Microsoft. I graduated spring 2020 from UCF. This is my first time presenting at Night Hacks. I've been to a couple Night Hacks events when I was a student, but this is kind of my first time really getting involved. So I'm excited to be here and introduce you guys to some Rust.
Yeah, the way Matthew got involved is I posted, Microsoft has, a bunch of internal chats, and we have an internal chat about Rust. And I asked for help, like, hey, what should I do for my school to introduce everybody to Rust? And Matthew hopped right on the chance to help. So big thank you to him. So, next slide. So here's the agenda. We're going to talk prereqs, already kind of discussed that, so we'll gloss over that next slide. We're going to talk about what Rust is, and at the same time, you're going to see why you would want to use Rust as we talk about it. Quick glance at some applications. Then we'll jump into Cargo. We'll tell you what that is, and we'll talk about some of the key features that make Rust Rust and why it's so cool. So halfway through the slides, Matt will take over, and he will start presenting the rest. So I'll do some live coding examples, and Matt will do the rest of the slides and the project at the end. So if you follow along with the live coding, and we do recommend that you have Rust installed on your system, it's by no means a requirement to participate, but you will get a really cool project at the end of this that you can slap on your resume. So I think you'll like it. I'm finding it exciting. So at least I did. I found it really cool. So all this stuff is in the links in the chat. If you're using VS Code, make sure you use the Rust Analyzer extension. Don't install the Rust extension. Just install Rust Analyzer. It is the less popular one by downloads, but Rust Analyzer is going to be the de facto moving forward. It's really good. And you definitely want it when using Rust on VS Code. It will help you out a lot. It really holds your hand, and it's just one of the great things we're going to talk about with like Rust tooling in the community. So why Rust? So what is Rust and why you would want to use it? So Rust is a systems programming language. They have a really nice motto, and I don't remember it. It's on the Rust Lang page if someone can copy and paste into the chat right now, because the community is great. But what is Rust? It's a systems programming language for everyone, essentially. It has really great performance. C++ level speeds are faster, and oftentimes it's as fast as C. You're often told C is the fastest language because it's so low level. Rust is very safe. So as you'll learn through the slides, Rust doesn't have a garbage collector like other languages like Python or Java, but it's still, you don't have to free memory manually. So if you're using C, maybe in your intro to C class, you have to like call malloc, and then you have to call free, and Rust, you don't do that. And we'll show you how you can get away with that, how you can have essentially no memory leaks in safe Rust and still not have a garbage collector. Rust is really productive. The tooling's great, the community is great, the compiler error messages are great. So oftentimes when you get an error message in a lot of languages these days, you kind of frustrate, you pull your hair like, no, why is it broken? I can't figure out why. That's not the case with Rust. We're going to error out on purpose a lot of the times during these slides, and you're going to see the error messages tell you exactly what's going on in plain English. The Rust community puts a lot of effort into having a very helpful compiler. And the syntax, while it is a low-level language, it feels like you're writing Python. You feel really productive with writing Rust because the tooling is so good. And another thing, like I said, it's suited towards system software, so like compilers, low-level programs, parsers, but you can use it anywhere. You can use Rust to write a backend. You can use Rust to write a front end for a website. A lot of frameworks are out around that. And you can use it for games. So speaking of which, next slide. So some of the applications for Rust, and we'll go over a lot of them. Firefox, so if anyone's used Firefox, like I'm using right now to present the slides, Mozilla developed Rust. A lot of security issues that came, I think, around using the browser were always memory related. So like a memory leak would basically let a hacker get through that door. I'm not too familiar with security, so I don't actually know why memory leaks basically correlate with exploits and everything. So I'm sure if someone else knows, they can write it in the chat. But essentially, Mozilla's like, we're tired of this. How can we solve this problem? And they developed Rust in like the early 2010s, and they open sourced it about halfway through, and it's been kicking off ever since. One thing that's mentioned when I think when Nighthawks announced this workshop, is Rust has won top language on Stack Overflow 5 years in a row. And you'll see why in a second. Dino is another cool application of Rust. So if any of you are familiar with JavaScript, specifically Node.js, maybe you've used Node.js in some of your classes or for some hackathon projects, the creator of Node.js, he was really unhappy with a lot of the shortcomings of the runtime. So he went ahead and made Dino. I'm seeing a lot of chat messages here, so I'm just going to have chat open. Sorry if I'm missing something critical. Feel free to just one of the hosts interrupt. But Dino, so the creator of Node.js went ahead and made Dino that fixed a lot of the shortcomings he found. It's right out of the box. It's suited for TypeScript, and it's written in Rust. It's really cool. And for a lot of people who like video games out here, Valorant is a really cool game. It's essentially Minecraft meets Cube World meets like Dwarf Fortress meets like really cool RPG, and it's all written in Rust. And the community around Valorant is also really cool. If you are interested in game development and you're also interested in Rust, that's a project you can contribute to yourself, and they make sure they onboard new developers really nicely. So lots of opportunities to use Rust, and lots of companies are using Rust and are hiring more Rust developers. So it's a great language to have on your resume. I should say neither Matt or I work on Rust for our day jobs. I don't know, maybe Matt does now, but I don't. I really do want to, so that's definitely one I want to take my career. And you'll see why when you get to use the language. So
yeah, ironically, I work on C++ static analysis, which is rendered moot by Rust's own compiler.
So you're going to be out of a job because of Rust. So I'm not pulling up the chat window. I want to have it on just in case. Cool. So Robert asked a really good question. Are there a significant number of Rust jobs these days, or is it still largely in a growth stage? I would say there's a decent amount. I think every time I've seen a Rust listing, it's always for like more senior engineers. But I went to Rust conference this past summer for RustCon 2020, and they were hiring a lot of new grads. So if you attend like conferences, they have like a bunch of job postings. And like Dropbox, for example, was like hiring like, hey, we want a bunch of Rust people. So anyways, let's go back to the slide. So Cargo, whenever you use a language, sometimes it might come with associated tooling. So if you use Python, you might be familiar with pip. If you use Node.js, you might be familiar with NPM. These toolings are essentially to help you run the language. They help you install new packages. For the Java world, there's like Maven and Gradle and stuff like that. So what Cargo is, it comes natively with Rust. So when you install Rust, you're going to get Cargo with it too, unless you install it some other route. And it's essentially, it's the package manager. So it lets you manage packages, which are called crates. And it lets also the build system for Rust. It's not the compiler for Rust. The compiler is called Rust C, but Cargo does the calls to the compiler for you. And it handles and basically helps hold your hand and simplifies a lot of things for you with just simple commands. Now, the Cargo is not just a build system. It also generates documentation. So I'll show you in a sec, like, why is that an advantage? Why do you want Cargo generating documentation? If you've ever needed to generate documentation for a project like Python, it is a nightmare to find a documentation solution. There's dozens of them. They might not work with your specific framework. It can be really annoying. Cargo, that's just built in. Everyone uses the Cargo doc generator, and they might have some add-ons depending on their use case, but it's great. You can run tests with Cargo. You can run optional linters for your program or style checkers, and you can also use it to install Rust programs. So if you have a cool Rust CLI tool, you can install it using Cargo as well. So before we kind of jump anywhere else, we're actually going to jump right into the code right now, really early on, and we're going to do a quick little demo where I'm going to show you Cargo, and I'm going to show you some basic Rust syntax. So I'll go ahead and I'm going to start with I'm here in the terminal. So let's go ahead and get started with Cargo. We're going to show you the whole Rust workflow to get started. So let's see, I'm going to make a directory called Rust. Actually, no, wait, I want to do this. So I'm going to do cargo init so that you can use the cargo init command to create a new directory and give it a name. And it also sets up all the Rust scaffolding for you too. I normally make a directory, then run cargo new init, but this is much more productive. Don't do what I do. Do as I say, not as I do. Rust first program. So we're going to write our first program in Rust. So it goes ahead and creates a little package for you. If you ever want to make a library, like if you want to make another, like a crate for a Rust project, you could do stuff like cargo lib, and it provides that tooling for you as well. So let's go ahead and change directory into this. So yes, good idea. The font might be hard to read right now. My VS Code is increased in font. Let's see if yes, perfect. The shortcuts are the same. I'm using Windows Terminal, which is also developed by Microsoft, and it's a really cool terminal program that you should use if you have Windows. So thank you for calling that out. Yeah. So I'm going to go ahead and open code from inside of here. And when we open code, what we're going to see is we already have a source file, and it's going to have a main.rust, which is just going to say hello world. So if we run that, it's going to say that. As a git ignore, so the target is the build folder. It's whenever you build your Rust program. Remember, Rust is a compiled language, so it's going to have a little target folder, and you don't want to be uploading that to your GitHub repo. It's going to also be big and hefty, and you just don't need that there. You have your cargo toml, which Matt will be talking about later. This is where you can add your additional crates down here, and your cargo lock, which is similar to package lock if you ever used NPM. Yeah, it doesn't initiate, I don't believe it initiates a Git repo. Correct me if I'm wrong here, Matt. Does Cargo new, I think if you have Git already configured on your system, it creates a Git repo and then it can let you push?
I'm not sure what it does if you don't have Git. It might just complain that you don't have Git. But it is ready for Git. Like the Git ignore is set up like you showed.
Yeah.
Oh, accidentally muted myself. You could try running a git status to see with.
I heard you. That's a good question. Let's see if I run git status. No commits yet. It does create a little local repo, it looks like. Okay, cool. Add a little local branch. So, excuse me for 1 second. I'm pulling up the example code I have on the side because I definitely don't remember everything off the top of my head. So let me go ahead and pull up that example code. Cool. All right, so I'm going to show you some basic Rust syntax. We're going to walk through it here. Let's get ahead and get rid of this hello world. As I'm running Rust, you're going to see these like gray, like this, you see this in gray. Obviously, I didn't type that. That's coming from Rust Analyzer. So it's going to help fill out a lot of stuff. And as I'm typing, you'll begin to see it. You'll see things I didn't type itself. And that's because Rust Analyzer is filling them out for me. So if you're following along on Rust Playground or on your own local machine, that is why. Don't type anything that's in gray, and you'll see why in a second. That'll make more sense once I actually start typing. So let's go ahead and let's declare some variables with Rust. So with Rust, declaring variables is extremely straightforward. We're going to say let. Let's do hello, and we'll give it a type. It'll be I32, and we could say let hello equal 10. So a few things here. It's not like other languages when you put the type before the variable name. This is easier. Like whenever you're talking about variables, you don't talk about it. Yes, my I32 hello variable. You say no, my hello, which is a type 32. It flows much nicer with language, and you'll see other languages like Python adopting this way of declaring types as well. And TypeScript, I believe, also does it this way too. So this is an int 32. This is, I think, a signed int 32. If you want to do an unsigned int, because that's what you want, you could just do u32. And you can also maybe, if you need less space, you could do an I8. Or you could do, I think it goes up to I128. Yeah, if you need that, you never need that much space. I don't think you ever do. So I might be wrong. There might be a use case for that. So we have this, we have a hello, and it's a int 32. And let's go ahead and let's just print it. And if you notice something right here, if I just do, let's just see what happens when I do this. There's an error, like, uh-oh, why can't I just print this? So, okay, this is where Rust immediately becomes really helpful, especially Rust Analyzer. If you're new to Rust, you might be other languages, you might just be doing like, let me print something. Nope, Rust Analyzer tells you, hey, that's not the function you want to use. In this case, it's called a macro, and we won't be talking about macros in this talk, but if you want to know what they are, happy to answer that question in the Discord. So it's a print line. So it's print line, and it's a little exclamation point. And you can tell something's a macro because it has that exclamation point with it. And this is not right, and we're going to correct that in a second. So if you're familiar with C, you're just going to use the familiar bracket notation, and the error goes away. So something's a macro because it has a little exclamation point at the end of it. A simple way to explain macros real quick, it's just a function that expands code. It's essentially, it's taking that thing in and it's going to expand it. It's more complicated than that, but we won't be getting into that. And you don't really need to know to start using Rust and making some cool stuff. It's a really cool thing you should learn down the line. So if we do this, it's just going to go ahead and print hello. So it's going to build my program and it just prints 10. So I don't want hello to be 10. I want it to be a different value. So let's say I want hello to be 11. Now we're going to be introduced to one of the first cool things about Rust. It's airing out here. It's not like, no, you cannot make hello 11. Let's see why. Cannot assign twice to a mutable variable hello. So this is one of the really cool things about Rust. All variables are immutable by default. And something like C or Java, you might call it like static or final to specify to the program like, hey, don't change the value of this variable. Rust, and by default, all variables are immutable. If you want to mute it, you just need to write mute. So, and then now I can change that to 11. And it won't complain. It'll let me run the program. And the great thing about Rust tooling is a lot of error messages that you would get in the compiler are just going to happen in the Rust analyzer. So let's take a look at compiler error message real quick. So if I run that, the compiler error message will give me the same thing Rust analyzer grades. Cannot assign twice to a mutable variable hello. So it's written in plain English. It's much easier to read. So let's say I don't want to change that. I want hello to be immutable. And there's more than one way to declare a variable. If you know, Rust can also infer types. So let's see, goodbye. And I'm just going to give it, we're going to give it 10 as well. Rust, if you could see right here, Rust already knows this is an int32. I didn't need to specify that. It can infer that by using a 10. And I think all integers in default by Rust are going to be int32. If I need it to be like an int8 because I'm on like a system that has like very low level, I can just call it an int8. Cool. So we're going to go ahead and we don't need these anymore, but I'll leave that here actually for anybody who's still following along in coding. Let's go ahead and let's make a vector. So a vector is just, correct me if I'm wrong here, but it's just an array that can be basically any size. It's a dynamically sized array. So something like an array list in other languages is a good way of describing it. Although I think array lists under the hood are often like linked lists or something. So we have this vector. Does anybody in the chat want to guess what happens if I type? I don't want to tell you what the answer is, but since I told you vectors can be dynamically sized, if I type v push 4, so we're going to push 4 onto this vector right here, what's going to happen if I uncomment this code? Is it going to run? Is it going to error out? What does the chat think? Okay, Rob thinks he thinks it'll work. Okay, so who else has any other thoughts? Okay, Chris says he'll think it'll work. Let me disable Rust Analyzer. So actually, Rust Analyzer is going to give the answer, but let me just disable it real quick so it doesn't tell you the answer as I write it here. So, and let's go ahead and run it. Cargo run. So you type cargo run to run. Uh-oh, it errored. So we'll talk about borrowing in a second, but remember, everything in Rust is immutable by default. So even this vector that's dynamically sized, you told me it's just going to be this size. So it's already, you can't mutate it anymore. If I want to change it, I have to type mute. If I save, and if I run this again, it's going to run without a problem. So it also printed the 10 from earlier. So it's going to run without a problem. This is, so if you remember earlier, I was talking about macros and just a little exclamation point. This is another macro to create a vector. There's another way to create a vector. So a vector is a type of struct, which Matt will be talking about later, what structs are. So another way of creating a vector would be vec and new. That's another way of creating it. That might be familiar if you're used to Java or other OOP languages. Okay. So Chris asked a good question. Can you change a value inside without declaring it mutable? I believe, Matt, can you answer this question? Is it, I think by default, no, there's no exception to that rule that if all variables or data are immutable by default, right?
There's a concept called interior mutability that you can opt into that kind of allows you to break that, where you can have like some outer object and still change the inner object even though the outer one isn't marked mute. I think in this case for Vex though that doesn't apply. So there is a way to do it, but it's kind of like advanced, and we won't really be talking about it right today.
I think Java and JavaScript, if you declare an object constant, you can still change the inside of the object. I think that is still mutable. And I think Rust operates like if you declare like inner members of the structs mutable, I believe, right? Yeah, so Rob is complaining that that's a lie. Yeah, constant is a lie. Yeah, yeah. So it's basically it's similar, but in Rust you have to declare that it's immutable. It's really nice. So we use this syntax. It's just like the syntax you might recognize from OOP languages. We're going to go to our first for loop. So for loop syntax is really nice and concise. This is similar to like the for, there's a name for it. I'm not remembering it right now, but it's similar to other for loops you might see in other languages like Python. So go ahead. We're going to push 10 variables to the stack. It's not going to push 11 because this is not inclusive of the 11. If you want it to be, you just do that, and it'll go from 1 to 11. If you go like this, it's going to go from 1 to 11 minus 1, so 10. So if you want to include the upper bound, you add another period. If not, you just think of it like that. So Rust also has a lot of syntactic sugar that makes stuff like that much easier to read and work with. So we're going to add 1 through 10 onto our vector right here. And now we're going to get into some really fun stuff. So can anyone tell me what the iter is? What is this iter? Okay, it doesn't tell me when I highlight over it. Good. Okay, Ricardo says iterator. Perfect, you got it first try. So iterators and iterables you might be familiar with the term from other languages. And one benefit of an iterator or an iterable, there's a bunch of compile time advantages that you get from them. So it doesn't have to do any like bounds. I think it eliminates bound checking. Is that right? It eliminates some bound checks. It can help speed up that loop to make it more performant. So yes, C++ does have these everywhere, and Python also has them too. So Python has the concept of generators and iterables. Iterators are great. There's a lot of fun stuff. You can do them in Rust as well. And we won't be covering all of those in detail, I think. But yes, that is an iterable. And so this is going to be one of my favorite features of Rust is its pattern matching. So let me go ahead and I'm going to copy paste this because it's a lot of typing and I don't want to spend the whole time typing here. So pull back chat up. So this is one of my favorite things about Rust is its pattern matching and some of the things that it takes from functional programming languages. So basically what we're going to do is we're iterating through this list that's 1 through 10. And every time, so we're going to start, I is 1, and it's going to print this. And I is either 2, 3, or 5, it's going to print this. You know, you can follow along if it's 6 or 10 or 9, et cetera, et cetera. But what is this right here, this underscore? You could probably guess by what it's printing here. So it's a default or a catch-all. Those are really good. Those are really good answers. Yes, so we are going to explain pattern matching in more detail, but just a quick introduction. This I is going to be an int 32. So 1 through 10, it's going to be integer 32. Rust wants to make sure your programs are safe, and it wants to it's like it's going to prevent you from pulling your hair out. And one of the ways it does this is it knows that, hey, 1 through 10, that is not all possible int 32s. You're missing like 4 and 8, and what if you have 11, and what if you have 12? And you're missing all these other use cases. So to prevent you from like kind of pulling your hair out later in production, Rust has this concept, like there's a bunch of other ideas of pattern matching, but one of them is just, hey, if I didn't specify like what the value is, just go here. And you can just have this do nothing if you wanted to. So if you just wanted it to just print nothing, maybe just print a new line, you could do that. So actually, if we run this code, we'll see when it got to 4 and 8, it just printed some new lines. There is a way to throw an error, yes. So we'll be going, I think Matt will showcase some of that, but if you want, you could throw an error here. It's not, I think in Rust, it's not really called like erroring or panicking. You throw an error You don't really throw, like when you say error, I think of throw something, I think of an exception. And Rust is called panicking, and it just kind of terminates yeah, we'll talk about that later. So I don't want to steal all of Matt's thunder because he has a lot of cool stuff to present. So this is our little first code example. I'm going to kind of speed along here. Whoops, wrong browser. So this is, we talked about the variables are immutable by default. It's really cool, pattern matching, iterators, all really cool stuff of Rust. But here's where it gets really awesome, is the ownership. Ownership, as the slides say, every single value in Rust has a variable that's called its owner. And then you can switch to what variables own what data. If you're familiar with a stack and a heap, we'll get into it in just a second. Every piece of data can only have one owner at a time. And this is going to save you a big headache from a lot of common memory errors that happen when more than one variable owns a piece of data. There's stuff like double free. So if you have in C, if you have X and Y pointing to the same piece of integer that's in memory, and you call free on X and Y, you're going to get a memory error because X already freed the data, then Y goes to free that piece of data, and it's going to just hey, you're telling me to free something that doesn't exist, and it just panics and crashes on you and complains. So this helps prevent a lot of common memory errors. And when the owner goes out of scope, which we'll show in just a second, the value will be dropped. So that way you're not biting yourself in the foot, like later on you declared a value X in this function scope, and then you want to reference X later, it won't let you do that, and it'll make sure you don't do that by accident. So, and it does a lot of other cool stuff too. So, and in borrowing, this is another really neat feature of Rust, and this is where the heap kind of comes and plays a big role. Whenever you want to let's say you have a variable and X, and X is a string, and hey, I need Y to be able to look at X, but I don't want Y to own X, and this is going to make more sense as I show in the code. Y instead can borrow X. It can be hey, I'm just going to use X for just a little bit. And what borrowing is, it passes a reference. You might be familiar with pointers. It passes a reference that can give you either, if you have a mutable borrow, is read and write access, and then an immutable borrow is just read access. So we're going to show what this is in a second, but a really important key thing here is you can only have one mutable borrow or any number of immutable borrows, but you can't have both at the same time. And this is, again, Rust is trying to save you from yourself. So, yeah, it is really cool. It's such a simple idea when you explain it out loud, but it really saves you so many headaches, and it just it's why people love Rust so much. It's not the only reason. I'm exaggerating, but it's whenever you learn about Rust, this is some of the first concepts you learned about is ownership and borrowing. And one thing I want to know, as you write Rust code, and Matt gave a really good example of multi-threading in the chat. As you write Rust code, one thing is that you're going to run into the borrow checker. It's going to kind of fight you a little bit. And everyone who learns Rust, this is perfectly normal. You're going to be fighting the borrow checker a lot. So borrowing in Rust, it's called the borrow checker. I never specified that. You're going to be fighting it quite a bit. That's perfectly normal. Using stuff like Rust Analyzer makes the fight a lot easier. And then one day it's just going to click. I still struggle with the borrow checker these days when I'm trying to write a little Rust program. So don't feel oh my goodness, Rust is so hard. It's perfectly normal. A lot of people have these hiccups when learning Rust. So we're going to go back into the code. Let's see. Oop. So you can also use cargo new instead of cargo init. I believe there's some minor differences between the two, but I'm not familiar. So I'm going to go made a new Rust package to use, and let's open it up in VS Code again. And I believe last time my code was not that visible. It was still pretty small. I'm sorry about that. Oops, that's too big. I think that should be good. So it's easier for everyone to read. So yes, race conditions are the bane of everyone's existence, Dylan. That's why Rust is so great. So we're going to go in some ownership examples here. So let's introduce ownership right off the bat. So we're going to do let x equals. I'm terrible at typing and also looking at my screen over here. this is just, and remember in Rust, the first rule of ownership is each value in Rust has a variable that's called its owner. So the ownership of 9 is X. So that's pretty simple, really easy, right? So let's introduce a new one, Y. So Y equals 4, and let's say Z equals Y. Cool, so Y equals 4 and Z equals Y. Let's go ahead and print these two out. I'm not doing any magic here, I'm just copy pasting code. But before we print these two out, I'm gonna modify Y. And kind of tell me what's gonna be printed in the chat. So if anyone wants to write what's gonna happen. I don't know why you're oh-knowing, Rob. Nothing bad is gonna happen, I promise. So what's, okay, so Rob thinks Z, yep, Dylan says Y is 5 and Z equals 4, and Y to have 5. Okay, let's see if you are right. Blanked out for a second. You're right, Y is 4 and Y is 5 and Z is 4. And the reason why, no pun intended, is because when in this line, when I say Y equals 4 and Z equals Y, since Y is I should have chosen much better variable names. Since Y is an int32, if we turned on Rust Analyzer, it would tell us this is an int32. It's a variable that's allocated on the stack. And the stack is something in it's a piece of memory your program uses that's kind of like a fixed size. If you're familiar with a stack data structure that you can learn at some of the coding interview practices that Night Hacks years, or you can learn that in CS1, you know that's something that's going to be from top to bottom. Think of a stack of pancakes, you kind of pull things off the top of the stack. Since it's a value that's allocated on the stack, what Rust does, since it's really cheap, to just copy it. So Z is just copying Y. So Y equals 4. Okay, let's just make a copy of it. It's not doing a reference. There's no pointer business going on here. That's all that's going on. So does anyone find that copy by assignment? I believe that's correct. I don't remember these terms anymore, and I just graduated last semester. I feel I'll have Matt answer the question in the chat there. So code I'm writing here is going to demonstrate. Thank you, Blake, for answering. It's copy by value, not copy by assignment. So what do people, so let's see, I'm declaring a new scope right here. Let's make this smaller, I'm so sorry. I'm declaring a new scope right here. So this is a little empty brackets. It's like, okay, here's a new scope. You can think of this as just like a function without a name, an anonymous function. And I'm saying A equals 5, and I'm gonna print A. What do people think is gonna happen when I do cargo run? Rob thinks it won't compile. Sure, let's see. You're right, it won't compile. So, and this is another great thing. So yes, this is scope. By opening up these brackets, you're essentially declaring a new scope. And if you need help thinking about scope, scope is just like where your program is in memory. And scope also plays into the stack. And there's some I'll send some resources afterwards that kind of visualize this for Rust that make it really helpful. It goes deeper than what we could do in this talk. So scope right here, this is creating a new scope, and A doesn't exist in this scope anymore. So you have the main scope, and then you have like your anonymous function scope, which is called, let's call it Mr. B. This is Mr. B scope right here. A doesn't exist inside of the main scope. But this is a really cool thing about Rust is help. A local variable with a similar name exists, X. So Rust tries to help you like, hey, did you mean X up here? Like, is that the variable you were trying to use instead? So this is another way the compiler just offers its hand right away. Like it can help you find typos. If you misspell a function name that's really similar to other function names, it tries to help you find those as well. So another great example of the compiler at work and all the awesome work the compiler team does to make the compiler really fun to use for everyone. So we can comment that out because that's not going to work. So I've been talking about variables that are allocated on the stack. Let's try something that's allocated on the heap. And the reason why strings and you'll see something like vectors are allocated on the heap, the simple answer is that they can dynamically grow in size, and the heap essentially lets you, it's not the stack that's rigid in memory. even then the stack's not rooted in memory per se. That's a simplification, but the heap lets you assign more data. And it's whenever you think of pointers and everything, I'm sure you might have learned this in Intro to C or CS1, a pointer references something on the heap. And I believe a pointer can also reference something on the stack. So we have this string value that's assigned on the heap. And let's see what happens. Cool. When I run this, what do people think is going to happen? So I'm trying to do exact same thing I did above, copy by value. I have this S1, and I'm trying to say S2, go ahead. I want you to also be hello. So Rob thinks 2 references to the same hello. Okay, let's see what happens. Ah, nothing. Nothing bad happened. Let's see what happens. Try to print it. Let's see, I'm going to try to print S1. So nothing happened there. Everything seems okay. Oh no! So here is something I kind of mentioned in the slides, but I didn't call it move per se. So yes, what happened? What is going on here? So if we go back to the slides, I clicked the wrong browser. So let's go back to the ownership slide. So there can only be one owner at a time. So only one variable can own a variable at a time. And since hello is allocated on the heap, and this is going to be where different move semantics, and this is where when I mentioned you're going to kind of fight ownership and borrowing and the borrow checker as you learn Rust, this is one of the reasons why. If we had Rust Analyzer on, it would tell us that this was an error and we wouldn't have to worry. Yeah, but essentially, when we assign S2, we're saying, hey, give us string 1. It's not copying this over like it did with the 4 for Z. What it's doing, it's moving this over to S2. It's the best way I could say it. It's essentially like, hey, S1 lived at this apartment number. It's now moving to this apartment number 2. Okay, Rob says, but it's immutable. We're not modifying anything about S1. We're just giving it a new owner. This was its first owner. You can maybe think of it as a dog. This hello was this Chihuahua, and the owner S1 is like, oh, I'm going to give it back to the shelter, and then S2 is going to take the dog from S1. I think that's a good example. I don't think that's the best one, but it's essentially what's going on here. You can't copy, yes, S1 is a very mean person. You can't copy a dog over. You wouldn't download your dog. So you can't copy the dog over. And we're not mutating the dog. This dog is perfectly okay. It's perfectly fine. We're not changing anything about it. So just even if we add immutable here, it would give us the same error. Value borrowed here after move. So we're trying to reference S1 again, and Rust is trying to stop you. So unlimited, we're going to show you how borrowing works in just a second, Rob. So we're going to get, that's a different syntax than what I'm doing here. So, and this is where the kind of things can get kind of tricky with Rust, as you might forget these as you go on. But we'll go ahead and comment this out because we want to use S1 later for later parts of the program. So let's actually get into, let's say, okay, I want to do a borrow. I don't want to take the Chihuahua from S1. We'll call this a Husky actually to make our lives easier. I don't want to take the Husky from S1. I just want to look at it on a pet cam. So, hey, S1, can I look at your Husky on a pet cam? Sure. Or 1, you can look at my Husky on a pet cam. Here, have access to my pet cam. Oh, this is a terrible analogy, but I'm just rolling with it. So this ampersand, you might recognize it from other programming languages. It doesn't mean the same thing it does in, I think, like C and everything. It's essentially giving you a read-only reference to S1. So essentially, it lets you look at the pet cam. So let's print it out here. We'll print S1. Control D does not duplicate a line like I was hoping it would. And we'll print out R1 and we'll see what happens. And look, they both print out Husky. This is okay. This is not, we're not copying it over. We added an ampersand. We're giving webcam access. So this is just an immutable borrow. This is what we call immutable borrowing. And I could do this again. So let's do it for R2. So we have 2 immutable borrows for S1 now. Husky, husky, husky. Wow. We're not making 3. We're not cloning the husky. R1 and R2 just have webcam access. They can look at the husky through their, I don't know, I bet Google has a product or something for this. I should be advertising Microsoft products right now. So, but let's see what happens when let's do a mutable borrow. So Rob asked, but wait, I thought you couldn't do immutable borrows of immutable thing. So these are read-only references. We're not doing immutable borrow yet, and I'll show you the syntax right now for immutable borrow. It's just going to be add a mute keyword. That's immutable borrow. But this is just a read-only reference. You're only reading what S1 has. You can't modify it. So you can't change what's in S1. So, and it doesn't matter if S1 was mutable or immutable. That's all you can do. So we're gonna try this now, and it's not gonna work. Uh-oh. Let's see what happens. And Rust, this is again, the Rust compiler is gonna, I could give this workshop just by erroring out on the Rust compiler and nothing else, and we can learn all of Rust this way. But what's happening here is you're doing a mutable borrow. So remember the ampersand and then mute keyword. And then for R2, you're doing an immutable borrow. And remember from the slides, I know this can kind of get tongue twisting all around. I want to close this. I'm so sorry. I keep opening the wrong browser. Remember that it kind of gets tongue twisty and everything. So you can only have one mutable borrow or any number of immutable borrows. And again, the syntax for an immutable borrow is just an ampersand. For mutable, you want to add the mute keyword. So that's one really neat thing. Another cool example, so I'm going to kind of show this, and then after we're done here, we're going to pass it over to Matt so he can finish off the workshop. And I'm sorry, Matt, for taking so much time. So I think I'll just end it right here, and Matt will go ahead and start taking things from here. And I'll be answering questions in the chat as Matt. I'll answer the rest of the questions in the chat, and Matt, I'll have you take over. And let me stop sharing my screen so we don't lose time.
Awesome. Thank you, Anthony. Yeah, let me go ahead and share my screen. So, oh dear, the Zoom thing's in the way of the, there we go. Can you guys see that okay? Okay. So we're going to talk about lifetimes. So this is kind of an advanced topic that's tied to ownership and borrowing. And it's one of the key things in Rust that prevents things like use after free or dangling pointers. Essentially what happens is the borrow checker, like Anthony discussed earlier, it can keep track of those scopes, like he showed in his example, for different variables and track if there's references that are referring to something that is about to go out of scope. So in this little image I have here, so we have A declared in this outer scope, the outer curly braces, and we have B declared in the inner scope, in the inner curly braces. And then we say A is taking a reference to B, right? A is borrowing B. Well, what happens is the scope ends and B gets dropped, right? B gets deallocated. B in this case isn't on the heap, but it's no longer on the stack either. That stack space is freed up as well. So when you try to print it, you're potentially printing something that has already been deallocated. So what lifetimes are is the way you annotate how long things live. And so here you might see the apostrophe B and apostrophe A. In Rust, those are pronounced tick A and tick B. So those scope, that inner brackets, that's tick B. That is the lifetime of B. B lives as long as that scope. And scope can be a function. Scope can be like this scope in here. It's just saying how long does B exist in the program. And the lifetime can also be the lifetime of the entire program. There's special syntax for that we won't really talk about. So what the borrow checker does is it looks at tick A, it looks at the lifetime of A, and it sees, hey, A lives for that entire scope of the outer curly braces. But B only lives for the inner one. You can't do that, and it keeps you from doing that. So you will have no situation where, say you call a function and you create some reference and you try to have something you try to have a variable refer to whatever that function returns, but it's not a pointer, it's not on the heap, you would have a dangling pointer, right? That thing from the function got deallocated, but you have a pointer to something that's gone. Rust doesn't let you do that. It guarantees at compile time that that won't happen. Most of the time, you don't care. Like if you'll see in the example, you see all that syntax for the lifetimes. Anthony didn't have to do any of that for his examples, right? And no one saw that, right? However, there are cases where the compiler doesn't know what you mean, and this ties a lot when you have references. So here, if you see that function call, this is the longest function. It returns the longer of the two functions, right? Well, there you see x and y are two references to strings. That's a special type, ampersand str. It's different from the string Anthony was using, which is allocated on the heap and growable. This str is on the stack, and it's a slice. It's like a view into memory, a read-only view of some string on the stack. And Rust doesn't know, because you have two different references and you're returning a reference. At the end, you see the other ampersand string. It doesn't know which one, how long should that thing you're returning live, right? Because both of these things are pointers to something in memory. Rust doesn't know, like, hey, are these pointers even still going to be alive? So the way you annotate that is you use this tick A syntax. Now note here that tick A, tick B, that's just convention. It can be tick whatever you want. Like in this case, you could call it apostrophe longest string and call each of those apostrophe longest string. Notice they're all the same in this case. What you're saying here, you're annotating the relationship between these references. You're saying this longest function, it exists for some lifetime A, and I'm going to guarantee that X has a lifetime A, Y has a lifetime A, so they live at the same time, they're in the same scope, and the thing I return is going to live at least as long as they do. And it will not outlive them. So if X and Y are gone, the reference you return is gone. You're basically guaranteeing to the Rust compiler, you're telling the Rust compiler, hey, this is what I mean. This is how long I want things to live. Now, like I said, most of the time you don't need it. When you do, it can get a little confusing. There's a way to get around it. Now, remember, all of this that we're talking about references, right? We're talking about borrowing, because the whole point of borrowing is to get around the fact that by default, Rust moves things, except for, like I32 and stuff like that. Most other things you deal with, they get moved ownership. So if you have some string s1 and you say let s2 equals s1, it gets moved. But if you don't want that, you do a borrow. Well, you can get around this. Simply, instead of creating a reference, why don't you just create a copy, right? If the data is cheap enough, it might be easier to just copy the data or clone the data and then pass it off to some function that'll take ownership, because it's just taking ownership of a copy. You still have the original, and that's totally fine. And in fact, that's what I recommend you do while you're starting out. I think when you first get used to Rust, and using references can be one of the harder parts of it, I recommend just not really working with references. Just clone things, copy things, that's a good way to not deal with the borrow checker as much at the beginning, because that can be a frustrating part. So I'm going to talk about structs. Structs are very similar to structs in other languages you might have seen in C, C++. They, like C and C++, well, actually more like C, or like C++. It's been a while since I've done C++. You define the methods on a struct separately from the struct itself, right? These aren't classes like Java or C# or Python. The methods are separate. So you define them in this block called an impl block. So you can see here impl player. That just means implement. This is the implementation of player. These are all the things, all the methods that player can do. Structs can also hold references. When a struct holds a reference, you explicitly need to put the lifetime. So you see down here we have struct player A. The name is a reference to a string, so you have to say that the player is going to live as long as that reference. Don't worry, we won't get too much into that. That was just to tell you that it exists. Now, one big thing about structs, different from other languages, is that structs, you cannot inherit properties from other structs like classes. Rust is not an OOP language. It has some things that look a little bit like OOP if you squint hard enough, but it is inherently not object oriented. So I can't have like a struct player and then I can't have that like have a parent class of like struct entity, right? That doesn't happen. The way you represent relationships between different structs, different types, is with traits, and we'll talk about that later. Enums are a very, very powerful tool within Rust. They're essentially a way they're called in functional languages is algebraic data types or sum types. They're different than enums you would see in C or C++, where an enum in C is just you have a list of things and they might be tied to a number, right? So you have just a group of different options. Here in Rust, an enum is something called a sum type. You can think of structs like a product type. So structs, essentially, they are this and this and this. So like that player example before, if I go back to it, a player has health and it has items and it has a location. An enum is an or. So here we have the option enum as an example. It is either some or none. But now, one thing you might see in this enum that's different from C or C++ is that enums can contain data. It's not just like some label. They have payloads attached to them. So in this case, this option, it's a very popular type. I've just redefined it in Rust. This is how you represent whether something is null. Rust doesn't have a null type, as Anthony described in the chat. Instead, you use the option type, which is an enum saying you have some thing. In this case, I've defined the thing is always a string, or you have none. You don't have the thing. Another popular one is results. Someone asked about error handling. This is how Rust handles errors. We won't get too far deep into it, but this result type says either this function is okay and you return the okay value, so nothing went wrong, or it's an error, and in this case the error contains a string and you can use that string. So we've defined this function here. I've called it returns option, and here's the syntax for accessing a particular variant of the option. So this function returns an option. It can either return some or none. In this case, I am choosing to return some, the explicit sum from option, and remember it contains data inside, and that data inside is a string. So I'm returning option some string, and now we go back to pattern matching that we saw earlier. The match operator can destructure enum variants. So notice where I have return match returns option. That means whatever returns option, whatever that function actually returns, here's what I'm going to do for each case. So in the option sum case, I'm going.
Matt, your mic cut out. Yeah, it cut out when you said in the option sum case. I cannot hear you still. I will let you know when I can. Oh no, I hope Matt is not still talking. Matt, oh no, Matt.
Hello, sorry. Yeah,
Yeah.
my headset turned off. Can you guys hear me?
Yeah, we lost you at the when you said the option sum case.
Okay.
So you were talking
for the match statement?
Yeah, you were saying in the option sum case.
Okay, thank you. Yeah, sorry about that. Yeah, so in the option sum case, notice that I can immediately bind the string that the sum case has to some variable. So in this case, I've called that variable string value. So what that is it's the match is destructuring the enum. It's pulling the data out. It's taking the shape of option sum, right? Because option sum has some data inside, and you can pull stuff out of it. In this case, I'm pulling out string, the string that's inside, and I'm saving it to a variable called string value, and then you can immediately use it. In the none case, I'm just printing that there's no string, right? That the none case doesn't have any data, so I don't do anything with it. Now, the cool thing about this, pattern matches are super, super powerful, is that this works for arbitrarily nested types. So that enum option, the sum case, could have its own enum inside that has its own data, that has its own enum inside that has its own data. And you can operate on that with match. Match can pull the data out deeper and deeper into the nested layers as you go. This applies to some structs as well. And just like Anthony said before, Rust will guarantee that you've handled every case of the enum. So in this case, we only have some or none, but option might have like some, none, maybe, you know, there could be a ton of things. Rust won't compile unless you do something for all of those cases. And again, you can just have the default, you can have the little default character. So here we're going to talk about how Rust handles sharing behavior between types. So like I said before, Rust is not an object-oriented language. You can't inherit things. There's no inheritance. Instead, Rust prefers traits. Traits are similar to interfaces in other languages, if you're familiar with them, where you describe some behavior that is tied to that trait, and then each struct implements that behavior. So, for example, here, I've defined some trait called can take damage, and it just has a single method associated with it called take damage. And what it does is, I'll talk about and mute self in a little bit. What it does is you pass in damage amount and it does something with it and it returns. That is the whole definition. So now I have these two structs. I have a human and an orc, and I want to say humans can take damage. I want something to happen specifically for humans when they take damage. So what you do is you write an impl block, but this time specifically for the trait, you're saying I'm implementing the can take damage trait for human. So for human specifically, this is what can take damage means. So when you say and mute self in take damage, it's a reference to the struct itself, kind of like self in Python or the this keyword in Java. So you're saying, you're basically saying, I'm taking a reference to myself and I'm going to mutate myself. Notice how different that is from C or C++, where if you call a function with a pointer, you don't actually know, or if you pass a pointer into a function, you have no idea if that pointer is going to change under you. You don't know if that function might dereference the pointer and do stuff. In this case, because of the function signature of take damage, you know explicitly that self is going to get changed. Something about self is going to happen. In this case, we're going to print human took damage, and then the health of the human is going to decrease by whatever damage amount is. Now the same thing for orc. I'm implementing it for orc. Now this case, it does pretty much the same thing, except we're printing something different. And now what I'm going to do is I'm going to write a generic function. So if you're familiar with generics from other languages, generics are essentially a way to tell some function or some struct that you can take anything. Like, for example, when Anthony created that vector earlier, right? He created a vector of numbers. A vector is a generic type. You can make a vector of strings. You can make a vector of, for example, here we have humans. You can make a vector of humans. You can make a vector of orc. That's a generic type. Well, this battle function, I only want things that can take damage. So I'm going to use something called a trait bound. And that tells this function that, hey, you can take only things that implement can take damage. So in this case, this function, I have fighter1, and I'm saying it's a mutable t, where t is a stand-in for whatever the type will eventually be. Now remember, at this point yet, before I compile, Rust doesn't know that the thing I'm going to pass in is going to be an orc or a human. It can be both. I could, since humans implement can take damage, I could pass in a human and a human. Since orcs can take damage, I can do an orc and a human, or I can do a human and an orc. And so what happens at compile time is Rust will generate the code specifically for humans, or specifically for orcs, or for orcs and humans. You don't pay any runtime cost for this. It doesn't figure this out at runtime. It figures this out at compile time. So as long as whatever you pass into that function implements can take damage, you can use it. And Rust will stop you at compile time if you try to pass in something that has not implemented can take damage. And here's another example of generics, where I have this weapon trait, and it just says that weapons can deal damage, and I have a sword and a bow. This is an empty struct. They don't have anything useful with them. But I want to implement weapon for sword, so I'm going to say swords, when you call deal damage in a sword, it returns 10, so it does 10 damage. And a bow does 7 damage. Now here's an example of a generic player. So before, where we had a generic function, here we have a generic struct, and it's saying that this player can be constructed with a weapon type. Anything that implements weapon, you can put as current weapon. And you can do multiple impl blocks for the different generic types if you want. So in this case, I'm saying when the player has a sword, when current weapon is a sword, you can spawn with a sword, and it'll print spawn with a sword. When you have a bow, you can spawn with a bow. And one thing that I forgot to mention during the structs section, the way you call methods on structs, there's 2 different ways. So here, where you have these methods that take self, they're called methods, like in other languages. You use the normal dot notation. So in this case, take damage, right? You can say new player dot take damage. But a method that doesn't take self as a variable, either and mute self, or you can also just do self, or you can do and self, ampersand self. This is called an associated function. It's like a static method kind of in other languages, where the function is associated with the type player, not with a specific instance of player. So in this case, new is a popular convention for creating a new thing. It's like a constructor. It doesn't have to be called new. It can be called whatever you want. And inside, there's actually syntax for building the constructor itself, or for building the thing itself. But a popular thing to do in Rust is to write a method called new. And you saw that with Anthony's example with Vec, and I'll go into that as well. So for these ones, we're not going to have a specific demo for each of them individually. Instead, what I'm going to do is have a kind of larger scope demo where we talk about a couple of these things. So does anyone have any questions before I get started with that? Are we all good? I don't see anything in the chat. So I'm going to stop sharing real quick. And what I'm going to do is, let me change what I can share. So can everyone see my PowerShell window?
Yeah, you're good.
Okay, so I'm going to init, and I'm going to call this project char map. And so it created this binary application package. And so I'm going to go to char map, and I'm going to open it up in VS Code. So let me set up my VS Code and show you guys what I can see. Okay, so you guys can see VS Code? Okay, great. So as you can see, VS Code created our source. It created our main RS. Actually, I want to move this out of the way. So what are we going to do? What's this project we're going to do? Well, we're going to create a CLI, a command line interface. And what we're going to have it do is we're going to read in a file, and we're going to count the frequency of characters in that file. And for now, we'll just print it to the screen. So for example, if I have some test file, and I just put in ABC, it'll print to the screen that we see A once, B once, and C once. And if I were to do ABC, B, C, A, you know, it'll just print out that we've seen A twice, we've seen B twice, and we've seen C twice. So like I said, for now, we're only going to print to the terminal. And what I want it to do is I want it to, at the command line, take some arguments of where the file is. Or it can be multiple files, in fact, where we can give it a list of files. So the first thing I'm going to do here is, unlike C, Rust doesn't have like argc, argv for getting command line arguments. It has a specific function for grabbing the arguments. So it's standard env args. And this is an iterator over the arguments. What I'm actually going to do is I'm going to turn that iterator into something that's a little bit easier to work with. I'm going to turn it into a vector. And so a way to turn an iterator into a vector is with the collect method. So what I'm going to do is I'm going to declare a variable here called let my args. And I want to collect this. I'm going to turn this from an iterator to a vector of strings. And put my semicolon there. And so now what this will do is it'll grab the arguments and it'll place them in a vector of strings. Now remember, vectors are dynamically resizable arrays. So now I have an array essentially of strings. And for now, let's just print them out. That's all we'll do for now. Okay, so one thing you'll see here is this error trips people up a lot at the beginning. Now, Rust is a really strongly typed language, right? It cares a lot about things being the right type. It's not like C where anything can be cast to anything else. It's not like JavaScript where types don't matter, everything's made up. In this case, this vec type doesn't implement standard format display. Now, what does that mean? Well, earlier I talked about traits, right? And how their traits define behaviors. In this case, standard format display is a trait saying, can this thing be printed? In this case, vec can't be printed. It doesn't have that implemented by default. However, it has another useful thing implemented by default called the debug trait, which means you can print debug output for it. So in this case, the way to do that, the syntax for this is a little funky, but it's a colon and a question mark. That means whatever thing I want to print it out in debug mode. So if I save, Rust Analyzer will update. And now you see we don't have an error anymore. So now when I try and print this, I'm going to cargo run. It'll build. I didn't give it any arguments. However, the name of the executable is the first argument. That's pretty standard in most places. So it just gave us the name of the executable, target debug char map, right? So now if I want to give it arguments, in this case, I'm actually I'm going to call the executable directly because passing in arguments from cargo is a little bit complicated and I don't want to deal with that right now. So I'm going to navigate to where the executable is. So it's in target debug. So I'm going to call charmap.exe directly, and I'm going to say myfile.txt. I've made up this file, right? So now when we print out the vector, we see, okay, here's where the executable is. Now it gave us the full path. And then we also see I gave it myfile.txt. Oh, I meant to ask at the beginning, is that a good size for everyone? Do I need to zoom in anymore? Can you guys see that okay? I'm going to assume we're good. I can't actually see the Zoom chat. I just realized. That's fine.
Yes, it looks good.
Okay, awesome. Thank you. So let's actually do something. Well, what I want to do is I want a way to represent the mapping of our characters to strings. So I want to have something in memory that we can kind of pass around, we can use for holding that data before we print it out. So I'm going to create a struct, and I'm going to call this struct char map. And what this is going to do is it's going to hold the file name of whatever file the char map was called on. And I'm going to make this a string. Now remember, string is also heap allocated. It can grow. And I also want the char map to have an actual mapping of characters to their frequency. So I'm going to use something called a hash map. Oh, don't want to call it. I'm going to call this. I'm going to call it character map. And this is going to contain a hash map of char to U32. Now, if you're not familiar with what a hash map is, it's a data structure that provides a really efficient way to find key value pairs. So think of an array where instead of indexing into the array with some number, if it's with its position, in this case we're indexing into it with a character. So you put in some character and it'll spit out what that how many times that character appeared. So we have this char map struct, and earlier in the struct section, I talked how there was explicit syntax for creating one by default. So let's make this char map. Let's actually, create an instance of this char map. So I'm going to say let my map equal. And so then to create one manually here, you say char map and then some braces. Notice here, Rust Analyzer has inferred that my map is a char map. And it's giving us an error saying, hey, you're trying to make a char map, but you haven't actually defined what file name and character map are. Well, the file name, I'm just going to call this test.txt. And you have to turn this into a string because raw string literals like this aren't capital S strings. They're string slices. You don't have to worry about that too much. Just know that if you're storing something as a string, call toString on it. That should relieve that. And then a comma, and then the next field. So character map. And remember, that's a hash map. I want to, since hash maps are heap allocated, I need to construct a new hash map. And so I talked earlier about how a standard convention is for things to implement hash map or implement new. The constructor is called new. And so now I have this new data type. And actually, in this case, I haven't imported hash map. It's not in the scope by default. So let me quickly fix that. There you go. You have to import hash map. The definition for hash map lives in standard collections hash map. So Rust kindly told me, hey, you haven't imported that. And now here it's saying, hey, I expect a semicolon. When you create a type like this, you need a semicolon at the end. That is a statement. And so now we've created this hash map. So now what do you think will happen? I can't actually see the chat, so if someone wants to say it out loud, what do you think will happen when I try and print the char map? Or sorry, I called this my map.
I mean,
Oh,
so I fully expect that it still won't work.
correct. And I forgot, like Anthony did, to turn off Rust Analyzer. In this case, yeah, it doesn't work. As we'll see here in the error message, char map also doesn't implement standard format display. Okay, so like I said before, let's just do the debug output. Uh-oh, char map doesn't implement debug either. Now, the only reason we could do debug for vec is because debug is implemented for vec, but we just created this char map. Rust doesn't know what char map has implemented because we haven't implemented anything on it yet, and it hasn't implemented debug. Now, we could implement debug ourselves, but it's a little bit complicated, and there's a lot of code repetition, there's a lot of boilerplate for that. I don't want to do that. Rust has this fancy thing called attributes that you can apply to different structs, different functions, and in particular, there's an attribute called derive. And what Rust will do is, looking at your struct or your enum or whatever, it will automatically implement something for you. In this case, I want debug to be automatically implemented for me for my char map. So I'm going to say, this is how you add one of these annotations. I'm going to say derive, and in here you put a list of things you want to derive. Now Rust Analyzer has graciously automatically said debug because that's a very common thing to do, right? I want to derive debug. So what Rust will do is at compile time, it'll implement debug for char map. And we don't have to worry about implementing that ourselves. So now, as you can see, the error's gone away. So now I have to cargo build and cargo run. In this case, we see the debug output for char map. So the debug output kind of formats it in a way so that we can see what the type is and all the inner stuff. And so we can see here that it's a file name where the file name is test.txt. And there's a character map, which is empty because we just allocated it. Now, so we've done that, and we can auto-derive debug. That's really useful for when you're first starting out, is knowing how to do that, because that can be like an easy thing to trip up on, is like, hey, I just want to get some debug output. I can't see anything in my struct. Just know that you have to slap derive debug on it. So now what I'm going to do is we're going to actually start implementing stuff on char map. So we make our impl block, and we say, first, the first thing we want to do is, similar to hash map, I think it's useful to have a new static method here, or an associated function, because there's actually some stuff that I want to do when you construct the char map. I don't want just this to be allocated in memory. One thing that might be nice is, when you try to construct the char map, let's actually check if that file exists in the first place, because if it doesn't exist, well, I don't want to do anything with it. So I'm going to comment this out, and I'm going to create a function called new. And what
Your mic.
my headset did it again. Sorry about that.
Okay, good.
What it's going to return is it's going to return self, which just means it's going to return whatever the char map is. This is useful instead of saying char map in case, like, hey, you change the name of char map, you change the definition of char map. Self will automatically figure out what you're talking about. So we're returning self, and the new function, what it's going to take in is, I want it to take in a file name, and I'm going to make that file name a string. And so what we're going to do is, based off the file name it gives us, first we're going to check, does that file exist? And then we're going to actually construct the char map and return it. In this case, you can see Rust Analyzer has told me, hey, I expected you to return a char map. I found parentheses. That means you return nothing. Parentheses are the unit type. It basically is representative for void, for nothing. In this case, there's nothing in the function, so I'm returning nothing. So let's actually construct the char map. So the first step is check if that file name, or if that file exists. So what I'm going to do is, there's a function for looking at the metadata of a file. It lives in standard fs metadata, and you give it a path. So in this case, the path I want to give it is the file name. And that's what I want to do for now. In this case, I'm actually going to do so that Rust analyzer stops giving me that error, I'm going to use a special macro called todo that just tells Rust like, hey, I'm not done with this yet. So standard FS metadata, it actually returns something called result. And I talked about that as one of the popular enum types. So result is how Rust does error handling. It's an enum type where you have the OK case or the error case. In this case, something might go wrong with metadata. So what if it isn't there, right? That's what the result is there for. If it isn't there, I'm going to return some error. If it is there, I'm going to return OK, and then I guess in this case it returns metadata. That's a special type. This IO result is a special type. And so we want to handle that, right? We want to actually do something if it goes wrong. So we're going to match on it. Remember, you can match on enums with pattern matching. So here it's saying, hey, you're missing an atch arm. So this is Rust guaranteeing that I'm covering all the cases. So the first case is OK. So if it's OK and we have some metadata, I'm just going to save it to metadata. I'm not going to do anything, actually. I just want to continue. But in the error case, so in this case, it returns error contains some data. So it's going to be E. Rust analyzer here is telling us that it's an error. Oh, I didn't mean to put a semicolon there. I'm going to, part of the syntax is if you're just ending a statement, you need curly braces around it. And a neat tool that Cargo has is auto formatting. So if I do cargo format, what doesn't it like? Oh, sorry about that. Yeah, cargo format doesn't work if you have compiler errors, obviously. I'll do that. Oh, okay, I need to handle the error case first. So in the error case, what I want to do is I want to call something called panic. And what this means is, hey, something's wrong, program needs to crash. So now I can format it so it looks nice. So this will basically just crash the program if it doesn't happen, or if the file doesn't exist. Now, this is actually a very popular use case. So popular, in fact, that Rust has some syntax for handling this. And it's called the Unwrap method. And this is implemented on result. And so what it actually does is it basically does what we wanted it to do earlier, where we do nothing with the OK case or we panic on error. So if I say unwrap, that'll panic when it fails. Now, that might be fine for testing out, but we don't actually want to throw that kind of error. We don't want to panic and just stop the program. We actually want to handle that result gracefully. So one thing we can do is we know that this returns IO result metadata. So we're going to return IO result, and I think we need to import standard IO. So we want to return IO result, but in this case, we're not going to return metadata. We just want to say that we'll return nothing if everything is fine, because this is, or actually, sorry, that's not true. We want to return self. So what we're saying is this function might error, and it specifically might have an IO error. But if it succeeds, it's going to return self. It's going to return a char map. So what we can do is we can match again, and we can say, okay, if it's okay, continue. If it's an error, return an IO error. But in this case, I don't want to handle the error right now. I don't know what to do yet if there's an error. So instead, Rust has syntax for easily passing the error back to main and saying like, hey, I don't want to deal with this right now in this function. You handle it, whoever called me. And that is the question mark operator, the try operator. That basically says, I'm not dealing this, I'm passing the error back. And now that's it. So now if we don't find the file at file name, it'll just pass back an error to main. So now that we have that, now I want to actually construct it. At this point, we know that the file exists. So I'm going to return self, or I'm going to create a char map. And I want the file name to be file name. And I want the character map to be a new hash map. And if you'll give me a quick second, I have to be right back. Sorry about this. Anthony, if there's any questions, you can go ahead and address them. Or if anyone has any questions, I'll be right back.
Yeah. At 9 o'clock, Matt must shed his crab skin. So it's once you become a Rustacean, unfortunately, every day at 9 o'clock you must become crab. So if anyone has any examples or questions.
I'm not sure saying that encourages people to learn Rust, Anthony.
I think if people wanted to become a crab. So Rob is asking, wait, so the question mark will return an IO result self? That is error? I don't see his code right now, so I'm not too sure.
Okay.
Like, there's a question in the chat for you, Matt. I couldn't answer it because I can't see the code. It's about the question mark. Okay, I missed it. Yes,
Yep.
He's asking about the question mark at the end of the file name.
Yes. So the question mark basically tells Rust, hey, this thing is returning a result, and if everything is okay, then we continue on as normal. Nothing happens. However, if the result is an error, is the error variant of that enum, so it couldn't find the file, this will return an error. We're saying, hey, I don't want to handle this right now. Pass that back to main. Because notice this returns a result, right? This is how Rust does error handling. We don't throw exceptions or anything. The type, the return type is an error. It's something that can fail. That is what result does. IO result is a special case of result. Results normally look kind of differently. But in this case, we're saying that there is some kind of IO error. There might be some kind of IO error. However, if there isn't an error, we'll be returning self.
Okay.
Does that answer the question?
So
yeah.
My understanding is it sort of fills the purpose of, like, normally you would like look up in like a more like conventional language, you might try to look up the file, and then if it was null, then you would know it didn't work or something. And so you would like check if it was null and then throw an error. And this is sort of a similar.
Yeah, in this case, the metadata function is telling us that there was an error, so it knew that the file wasn't there, basically.
Okay. And then if it didn't work, we exit, or the question. So that's like almost like control flow. Okay. It like exits. Okay.
Yeah. So in this case, actually, it won't exit the program, but it will exit the function really early. And
right. It'll return back IO result error that is the error one. Okay. Okay. That makes sense. Thank you.
Yep. And so eventually when we get to main, we'll have to handle that. But I'm not going to worry about it right now. So yeah. So thank you for the question. That was great. So in this case, yeah, we've constructed the hash map, or we've constructed our char map. We gave it a file name. We've allocated a new hash map. Nothing's happened yet, right? We've just created a char map for the first time. We don't want to do anything with it yet. We just know that the file exists. So now what we can do is we can either return char map, or remember, actually, well, we'll see what happens. We're going to return char map. Now, Rust is giving me an error here. Why do you guys think this isn't correct? Before I hover over it. Does anyone have any ideas? For some reason, I can't see the chat. So if someone is saying something in chat, I am sorry.
Oh, is it?
Oh,
it's
there
going
we
to
go.
fall out of scope, right? And then get deallocated?
So actually, in this case, because we're returning self, we're not returning a reference. Rust knows that it's going to move the ownership into whatever called new. So in this case, it won't actually fall out of scope. And that's a good question, because in C or C++, you might not actually know that. But Rust at compile time guarantees it knows that you're moving the ownership of this char map to whatever called the function.
Okay.
That was a good guess. In this case, it's not immutable. If we remove the return statement and the semicolon above, will the error disappear? Let's see. So I'm going to remove the return statement. I'm going to remove that semicolon. And I'm just going to put char map. Oh, sorry, my caps lock is on. So in this case, we still actually have an error. We still do need that semicolon because creating some struct is a statement. So that needs a semicolon. But if you see here, what's actually happening is Rust is telling us what's wrong. It's saying, hey, wrap the return expression in OK. Remember, this is returning a result. And a result is either OK and something inside, or it's an error with some error. So char map itself doesn't fit what a result is. We need to say we're returning OK char map. Now notice something else funky here, right? What looks weird about line 18? Does anyone have anything they'd like to point out, or just something weird about the new function in general?
Do you want to read the chat to you, Matt?
Oh, I'm sorry. Yeah, that keeps disappearing when I click.
I'll read. People are saying no semicolon or return statement.
Exactly. Yeah, very good. We don't have an explicit return statement. Now, the reason why is because Rust is inherently expression based. Instead of things being statements, a lot of things being statements, this, for example, is a statement. Functions in Rust are expressions. A lot of things are expressions. If statements are expressions, for loops are expressions. So what that means in the case of Rust is the last thing returned in an if statement, in a match, is the last line of whatever that expression is gets returned implicitly. So a funky thing about Rust is you don't actually need to explicitly say return here at the end unless you're returning somewhere earlier. But if you're, like in this case, the OK case where you're making it all the way to the end of the function, you can just say OK char map, or whatever your return type is. You don't need a semicolon. You don't need a return keyword. Return keywords are only for early returns. Let me see if I can get, if Zoom will pop up the, okay. I can see the chat now. There we go. So we've handled the new case. So let's try calling it. So what I'm going to do is, this will be very similar to how we see what we did with Vex. So what I want to do is for every file in the arguments, I want to create a char map for that specific file. So we're going to iterate over the vector of arguments. So I'm going to say for file name in my args. Now remember, hang on, sorry, Rust, give me an error here. Oh, this is a good point. Use of moved value file name. Now remember, we get this file name string, and I'm putting it in here, and Rust is saying, hey, we already moved that. So if I run cargo check, it should give us a better view of what's going on. It's saying, hey, you moved file name. When you called standard FS metadata, you moved file name into it. You gave it file name. We don't want that, right? Yes, Robert, that's a very good point. We want to just lend it to FS metadata. So we want to give FS metadata a reference to file name. So I'm going to put an ampersand here and save it again. And as we can see, that error is gone, because now we gave FS metadata a reference, and then it returned ownership back to us. So we temporarily gave it we temporarily gave it a file name. It gave the file name back to us, and now we can use it again. So now file name has been moved into the char map. So in this case, when we call the new function, whatever file name we pass it won't be usable back in main unless we explicitly say we want this to be a reference to a string. In my case, I know that I'm not going to be using that string again, just because I've written this before and I know that I'm not going to use it again. But if you didn't know, maybe you would want to pass a reference here instead. So we want to say for each file name in the arguments, I want to create a char map of it. So I'm going to say let cur map equals char map new. Notice we created that cool new function, and I'm going to pass file name into it. In this case, we're going to iterate and make a bunch of char maps. So I actually want to collect all of those. I want to hold those in a vector. So I'm going to say let maps equal vec. Oh, sorry. Let maps vec char map. So remember, vec is a generic, so it can take anything. So in this case, I'm making a vector of char maps, and Rust can handle that just fine. Is equal to vec new. And so this will allocate space for a vector of char maps, and it'll initially be empty. And I want to add that to maps. So I want to say maps.push cur map. So what's going to happen here is cur map is going to get moved into the vector. So this variable cur map, the data of that char map gets moved into the vector, and now this cur map variable no longer has ownership of it. I can't use cur map again because I'm explicitly passing ownership, which is really great because now cur map, for whatever reason, can't deallocate that char map from under me. Like some other thread, for example, can't go and change the char map, and then when I look at it in the vector, it's different. So Robert asked in the chat, so does this extend the lifetime of cur map? Essentially, yes. When it's moved into the map, it is now tied to the lifetime of the vector itself. So one thing that's going to happen here, we're going to see, is I'm going to save, and it's going to complain about this. It fed expected a char map. Oh, sorry. Yeah. One thing I forgot to do here is I forgot to actually handle the error. Remember how this is returning a result self? This might error out, right? What if it doesn't find the file? And Rust tells us at compile time, hey, you didn't handle the error case. In this case, what I want to do is I don't want to do anything with the error case. I just want to, if it errors out, it errors out. It's fine. I'll pass it back to main. I could match on this, right? I could write match char map new, and if it's okay, do something. If it's error, do something else. In this case, I don't really want to deal with that. So what I'm going to say is main is going to return the same type. It's going to return IO result. And in this case, if everything goes fine, main isn't going to return anything. But if there's an error, it'll return an error back to the terminal. And I'm going to put an OK here just to say that, hey, if main gets down here, everything's OK. You can think of this like returns or like return 0, exit 0 at the end of this. It's basically just saying that, hey, everything is fine. The actual error I wanted to get to was, there we go. So now I can use that syntax again, because this returns an IO result. And I'm going to say main doesn't want to handle it, so it's going to pass it back to whatever called main. In this case, it'll pass it back to the terminal. The actual error I wanted to get to is here. I'm trying to push something, but I didn't actually declare maps as mutable. Now remember, you have to explicitly make things mutable. Things are not mutable by default. So I'd say mute maps. So now we can push things onto that vector. Now, one thing that I said earlier that you may or may not remember is that when Rust collects the arguments passed to it, the first argument is the name of the executable itself, right? And we don't want to work on that. We don't want to try and open that as a file. It's not a real file, right? We know we'll error out. So iterators have a handy thing where you can do, I'm going to explicitly get the iterator for a vector, and I'm going to say dot skip, and I want to skip the first thing in this iterator. So it skips the first n elements. You can see here Rust Analyzer handily puts the docs here for you. I'm going to skip the first element, which I know is the name of the executable. In this case, it's not 0 indexed, which can be a little confusing. But remember, it's skipping the first n elements. So if you skip the first 0 elements, that's the whole iterator. So I just want to skip the first one. And so I'm going to make a char map. Okay, yeah. So one thing here that Rust is telling me is when I have this iterator, it actually takes a reference to a string. It doesn't take the string itself. So you remember how earlier I said, hey, I don't want to, I want to move it in here. In this case, the iterator, the for loop only borrows the string. It's not going to pull it out of the vec. So I'm actually going to do what I said I wasn't going to do earlier. And I'm going to take a reference because I know I'm only operating on a reference. And in this case, I'm just going to clone the file name. Now, remember I said earlier, if you don't want to deal with borrowing in lifetimes too much, you can just clone things if they're cheap. And in this case, the file name is a small string. I'm not running this on an embedded system. I'm running this on my computer. I have a heap. Some embedded systems don't have a heap. You can't dynamically allocate it at all. In this case, I'm just going to clone it because I don't want to deal with putting lifetimes for references here. And yes, you're right, Robert. It was basically calling iter under the hood when it was just my args. To be specific, for loops by default call iter on whatever iterable you have. So in this case, vector is an iterable. Yes, that's a very good assumption. There is an iterable trait. You can implement iterable on your own things. If you make some collection, you can implement iterable on it, and for loops will work just like they do for vectors, for hash maps, anything, that syntax will just work. That's a fantastic question, Robert. That was a good kind of segue into that. So in this case, I've sorted out all the borrowing things. As you can see, this is kind of what the process of is like of fighting the borrow checkers. Like, it's really not fighting. It's more like Rust is telling you, hey, buddy, you maybe don't want to do that here. You might want a reference. So we're going to iterate over that, and we're going to create a char map. And in this case, I just want to see what all of our char maps look like. So I'm going to print. I'm going to just print a debug print of our whole vector. I'm going to print maps. And I'm going to cargo build again. And now remember, I want to pass these in at the command line. So I want to do charmap.exe. And first, let me give it a file that doesn't exist, just so you see what the error case looks like. I'm just going to say not exist.txt. And we see the error, whatever internally that error looks like, gets printed back out to the terminal. So we see error, OS code 2 kind not found. The system cannot find the file specified. So that's what the raw error looks like from IO result. If we wanted to make that prettier, we could manually match on charmap new and have some different output. In this case, I don't really care about that. I'm just going to return the file name, or I'm just going to return that error. So I'm going to give it an actual file that exists, which is test.txt, which I created earlier. Did I delete it? Oh, I called it testfile.txt. And also, it's testfile.txt. It's also not in this directory. You'll notice here that I'm in Rust Workshop target debug. It's actually 2 directory levels up. So I'm going to go to that. And so we see now here, it created a char map. And remember, it doesn't do anything yet. It only created the new char map. We didn't actually call any of the methods on it. We haven't actually done the part where we do the mapping of characters to the characters to their frequencies. So let's actually implement that now. So what I want to do is I want to implement a new function. And so this one is going to be an actual method. This one you call on an instance of a char map. This isn't going to be an associated function. So I'm going to call this the count chars method. And what I want to do is I know that I'm going to start filling in this char map. So I'm going to mutate the char map I'm operating on. But I don't want to take ownership of it, right? I still want the char map to be usable after this method is called. So I'm going to make it a reference, and I'm going to make it a mutable reference to self. Now, if I just said and self, I wouldn't be able to actually fill in this hash map. If I just said self, or if I said mute self, I could fill in the hash map, but now whatever calls this method has lost ownership of the char map. So if I called, map.countChars, the main function can't use the map anymore. So I want a mutable borrow, and it doesn't take anything else in, right? Because this is just going to operate. We already know the file exists, so we don't need any other parameters here. And this is going to return nothing, because this is gonna modify the char map in place. We're essentially passing self by reference here, if you're kind of used to that from C. So what I want to do is I want to read the file into a string. And luckily, Rust knows that that's very popular. So that's something that I'm going to, or that's something that it has built in. So I'm just going to call what Rust has for that already. So that function is standard fs read to string. And you just give it the path. So in this case, the path is going to be, now I'm going to pass in a reference to the path because I don't want to run into that issue I had earlier. So it's going to be a reference to self.filename. And now read to string actually also returns an IO result, because Rust doesn't know that I already checked that the file is open. So this might error out as far as Rust is concerned. So I'm going to do the same thing I did before, where I'm going to have this return an IO result of nothing. So if everything is okay, it'll return nothing. Otherwise, if there's an error, it'll return error. And again, we have the handy question mark operator. And I want to save this to some string. So I'm just going to say let file contents string equals that. And again, I'm going to use this nice to-do macro so that it'll tell Rust Analyzer, like, hey, I'm not done with this yet. And so what this does is it'll read the entire contents of the file into this string file contents. And now I can do stuff with it. In this case, I want to do a hash map of each character to how many times it appears. So what I want to do is I want to iterate over the string. Luckily, Rust also has a built-in iterator for the characters of a string. So I'm going to say for cur char in file contents dot chars. So this will return an iterator of the chars, and it'll return Rust Analyzer here is telling us that it returns the actual char itself. What I want to do is, well, the hash map is initially empty, right? We don't know if the item's in here yet, right? So we want to check first is if self dot character map. So I'm going to check, does this thing exist? And in this case, I don't remember what the exists function is, right? How do I know if this thing is in a hash map? So what I'm going to do is I'm going to pull up the docs for hash map. Let me close this. And I'm going to change the share over to the documentation, just so you guys can see what documentation looks like. It's really good. So here's the documentation for hash map. It has a bunch of really great examples. The examples are also checked to see if they compile. Cargo doc does that by default. And so in this case, we see here, like in this example, hey, we have a contains key method. So I'm going to go ahead and use that. So back to my VS Code share. So I'm going to say if self.characterMap.contains key, and the key in this case is going to be the character, then we know that the char was already put in there. Oh, I see I have a question in the chat. If it will open up. This is doing the thing again.
Oh, they're just mentioning like logistics and everything. There's no questions.
Oh, okay. So if it's there, we want to update the frequency. So I'm going to say self.characterMap dot the frequency. I can insert where is it here in the documentation? The entry API. So what Rust provides is an easy way. So as you can see here, like the thing I was doing was kind of cumbersome, right? Like I'm checking if it exists and then I want to update it. Otherwise I have to create it, right? So I'd have an else clause here, and where I have to insert the thing manually using the way insert was showing before. There's actually an easy API for kind of getting past all of this, where I want to say self.characterMap.entry. So what this does is it'll return the key value pair in an easy way for me to update it. So the entry is going to be char. And I want to say if the char isn't there, we have this or insert method 0. Otherwise, plus equal add to 1. So let's unpack this. Oh, and Rust is giving yeah, let me dereference that. So well, first let's unpack what's happening here. So the entry is saying, hey, for this key, get me back the key value pair. Or insert is saying, if it doesn't exist, put in a 0. And then when all of that is done, I have a reference to that value in the map. And I have to dereference it because it returns an ampersand reference. And now what I'm doing here is we know there's already a 0 here, right? Because we just inserted it as a default. If it wasn't there, I can now add 1 to it. Otherwise, if it was there, it doesn't call this or insert. It just uses whatever value was there before, and it adds a 1. In this case, instead of char, I actually want to use cur char. But that's just a quick way of inserting that cur char into the map. And if it's not there, it'll handle that case for us as well. So now that I've done that, the map gets updated. And we can just say, OK. Nothing happened. And so now everything is fine. So we iterated over the file contents. And for each character in there, we updated the hash map. So the key was whatever character we're looking at in that file. And the value was some count of it. So in this case, we see A, and it's not in the hash map. So we insert a 0 and then add a 1. So now A is 1. And then we do the same thing for B, C, and then B, C, A. So we want to call that on every char map we create, because remember, we're doing this for each file. If I have multiple files, in this case, I'm only working with one, but I can pass in more, and I'll show you that. So now we push it on to the map, and actually, before we push it on, I'm going to make cur map mutable, because remember, this function takes it by and mute self. It takes a mutable reference. So since we're going to mutate it here, I'm going to say cur map dot count chars. And remember, it returns. My headphones did it again. I'm sorry. It returns a result, so it might error out. So we're going to say that, hey, if this happens, pass it back. And so this will count chars, and now we'll print out the map. So now, if I build this again, and I run the same thing that I did before, we now see, well, there's a new line character, right? Because I hit enter somewhere around here. There's a return character. Actually, the return might be the new line, /n might be just the end of the string. And then we see 2 A's, 2 B's, and 2 C's. So, so we've created a little CLI that'll take this file and it'll print out the frequency of the characters in it. And I can give it multiple files. So if I go here and I create another file, I'm going to call this file2.txt. I'll just put in this is a test file. I can call this CLI again, and I'll also give it file2. And we'll see here, so for the first file, for testfile.txt, it'll print out its characters. And then here we have another char map for file2.txt, and it's printing out the frequency of the characters in that file as well. So now we have a simple little CLI that'll get us the frequency of characters. So I see we're kind of running low on time here. So if anyone has any questions, feel free to ask them now, any kind of final questions. In the meantime, while we have a little bit of time, oh, I see Robert asked, why exactly do we need to use the star? I don't know if I answered that for you already, but entry returns a reference to something. So here in this example, you can see that I want to, if you want to change the actual thing, entry returns a reference to the value that was in there. It doesn't return the value itself, it returns a pointer to it. So just like in C and C++, you want to actually follow that reference to the data. So we're dereferencing it, because remember, hash maps are heap allocated. So we're going to the heap and saying, okay, whatever value was there, I'm going to change it. Does anyone have any other questions they'd like to ask? There's a couple more things that you could do with this. One thing I guess I can show real quick is generating documentation. If I want to generate documentation for this, you can say cargo doc open. And so it'll build documentation. And what it actually did is if I switch over to my screen here, it generated some documentation. Now the documentation here is empty because I didn't actually write any comments. But if I go back to VS Code and I say, like, I add some documentation with documentation 3 slashes, I say this is a char map. And then I do the same thing again. Switch my share back to here. We can see now that my documentation was automatically added and it was rendered in my browser. It creates an HTML file for you. And when you upload a library to crates.io, Rust packages are called crates, it generates this for you. So all of your code, as long as you put comments in it, documentation comments, this documentation gets nice and rendered for you. So with that, I'll probably wrap up here. Yes, there are multi-line comments, I believe. Let me verify that. I haven't used them. Yeah, you can do multi-line comments. I don't use them very often. And yes, normal comments are just 2 slashes. And you can add dot comments to each of these individual fields. You can add dot comments to each of these methods, to the implementation. Commenting and docs are really easy in Rust. And that's one of its awesome core strengths, is that it makes that really easy to use. So some optional things you can kind of follow up on if you want to take this example, and I'll be uploading this code later to the place where Anthony put it, is what if instead of printing to the terminal, you want to print to a file? Maybe add that as an option. Now, a good thing for making command lines easier is a crate called struct opt. So you might want to look into that if you want to add a command line flag to say, hey, I don't want to print to the terminal, I want to print to a file. Look into struct opt. Another thing you could do is, what if instead of a file not existing and then just returning and panicking, just handle that case and skip it. So you might want to do something like that. So I'm going to end this part here, and I don't know, do we have enough time to go through the wrap-up slides, Christopher, or are we out of time?
No, you can go ahead and go through those.
Okay, so sorry I went a little bit over. Hopefully you guys got value out of that example. And you can implement something like this later. This is a good starting project. It's making a CLI. Rust makes it very ergonomic. So going back to the slides, let me go ahead and share this again.
While you're going to the slides, Rob has put the link to our feedback form in the comments. Please, everybody listening, make sure to fill out that form. It really helps us inform future workshops.
Yes, it has been revamped, and like it's very like all you need to do is rate the workshop from 1 to 5. If you have other comments, of course you can add them, but all you have to do is rate it from 1 to 5. So please fill it out. Thank you.
Awesome. So what do we want you to take away from this workshop in Rust? Well, one key thing is that Rust brings a lot of new concepts to the table. You know, we have ownership, we have borrowing, and we have lifetimes. And while they're tricky concepts, this actually makes systems programming, especially without a garbage collector, more accessible and empowering than ever before. And the reason is, all of these things, ownership and borrowing, even though we call them novel concepts, they are things that C and C++ programmers have to worry about, right? They run into use after free bugs all the time. Keeping track of lifetimes, they have to do that still. The difference is they have to do that in their head. Rust does this for you at compile time. That's the key thing about Rust, is it turns runtime errors into compile time errors. So Rust will not let you make mistakes, which actually opens up systems programming to a wider field. You know, people who normally do front end, they're getting really into Rust because they're not scared of like, I accidentally segfaulted and bricked this machine or something. Normally, you know, that won't actually happen, but it's a lot more accessible. Another thing we want you to take away is spending time with the basics. Ownership and borrowing, you probably haven't seen in other languages, and it actually pushes up front how complex things really are. So we recommend really sitting down and trying implementing a CLI like we did here, but not doing anything super complex at first, like implementing your own data structure. Here, I call out linked lists and graphs. One thing you'll find out is linked lists and graphs, while you learn them really early in CS1, they're actually super memory unsafe by default. They allow you to do a lot of things that Rust doesn't want you to do. So we don't recommend trying to write a linked list first. There's a whole website here about what it takes to write a safe linked list, and it goes in very high detail about why it's a bad idea. But start with the basics, you know, really get used to what ownership, borrowing, and lifetimes are, so that way you can move into more advanced stuff without fighting the borrow checker. Another thing, read the error messages. The error messages are fantastic. Rust has really, really great error messages. They put a lot of effort into it. And the compiler, you want to work with it, like I said earlier, like it's a friend, it's a peer, it's giving you advice, it's peer programming with you. It's not there to stop you from doing what you're doing. It's there for stopping you from making a mistake. And kind of like I said in the lifetime section, references and lifetimes can be tricky. So at first, I recommend just not dealing with them. Like, it's fine to copy and clone stuff everywhere. Like, that's totally okay when you're first learning out. Or, you know, if you're dealing with error handling, it's fine to just call .unwrap and panic if something goes wrong. Like, you don't have to, you know, return IO result like I did, or the normal result type. It's totally fine to copy and clone. Don't be afraid to use things like vec or string instead of ampersand stir. Or in here, I don't think we talked about this, but ampersand and empty brackets is a slice. It's basically a read-only view into an array or a section of contiguous memory. Don't be afraid to use vec or string instead. Like, yes, it takes more memory, but for a lot of cases, that doesn't matter. But the reason there's a distinction is because Rust wants to be a systems programming language. It wants to be used in things like writing a kernel where you might not have a heap. It wants to be stuff like a bootloader where the rest of the operating system hasn't even loaded anyways. You can use it in embedded. That's why there's that distinction, but you don't have to only use it in those cases. If you're writing a CLI like I was, throw strings, throw vex, use those larger memory types because they make it a lot easier for you to learn Rust without really banging your head around ownership, borrowing, and lifetimes too early on. So another slide we have here is some cool resources. There's the Rust programming language. It is a free book. It is awesome. It is kind of the first place you want to direct anyone to learn Rust. It's online, or you can buy a paperback copy. There's Programming Rust, which is an O'Reilly book. It is useful for those with C, C++ experience. It assumes you have kind of that, and it talks a little bit more about heap and string or heap and stack and the different things you might have seen in C++ with multi-threading. There's John Jengshet, I think that's how you pronounce his last name. He does intermediate to advanced Rust streams. So if you already know Rust and you're kind of checking out the workshop, there's some cool stuff he does here. Ryan Levick from Microsoft, he does a lot of great beginner streams. He goes more in depth, and he has a similar CLI example than what I did today. Now Shemerel Harrington, another Microsoft employee, she has a lot of cool videos from talks that she's done before. In this case, I linked the traits deep dive, which is where I got my warrior struct orc example inspired by. And there's the This Week in Rust newsletter. So there's cool Rust projects, jobs, like it just links to a bunch of really cool things that's been happening in Rust. And that's it for me. Thank you so much for following along with that CLI and for following along with Anthony and I on this Intro to Rust workshop. I don't know if we have time for any more questions, but go ahead and ask if you have any. Otherwise, I think we're pretty much done. I don't know, Anthony, if you want to add anything.
No, yeah, thank you so much, everybody, and thank you for sticking with us. We know this was definitely a longer workshop than normal. It's really hard to cover like Rust, and we were debating for a while, what should we include, what should we not include, and we're really just touching the surface with what the language has to offer. And the great thing about Rust, I just want to add, is like the community is fantastic. You will not find another like enthusiastic community for a programming language like anywhere else. Like the community is super diverse. Everyone's super friendly, like they're always ready and happy to answer your questions, and there's tons of learning resources throughout the community. Definitely check out This Week in Rust. It's super fun newsletter. I love every Friday. I think it's published Thursday night or Friday morning. I look forward to it, and I definitely check it out. So yeah, definitely, there's plenty of awesome resources, and definitely keep exploring Rust afterwards. It's really fun.
Awesome. Are there any other questions? Okay, thank you so much, Matt and Anthony. Really interesting workshop. I learned a lot. And thank you everybody for coming. We'll see you next week for our How to Get into Grad School. All right, bye-bye everyone.
Bye everyone, thank you.
Thanks.